So, good evening, everyone. Welcome to week two of live problem solving session for the analog electronics circuit course. So, in today's session, we will be talking about MOSFET and we will be solving problems based on MOSFET. Okay. So, first of all, we know that MOSFETs are active devices. We discussed a lot about this in last session. And what are the number of terminals that I said that are present in the MOSFET? So those are gate, source, drain, and body. So P, B, and P. Now, in these four terminals, let's say there can be two conditions. So source, drain, gate, these are the active terminals. Or we can say mandatory terminals. Like these are must. Okay. When it comes to body, there can be two conditions present. So one is source body shorted. So if this is the situation when source terminal and body terminal are shorted, there won't be any issues in the MOSFET. MOSFET will work fine with certain VTH percentage. Okay? Now what happens? Let's say while designing, what you do, you don't short source and body. So source and body are, let's say, separated. Okay. So in this particular case, it will lead to VTH shift. So it will depend on what type of potential the body terminal observes. Based on that, your VTH will shift. So either it can shift towards positive or towards negative side, so, or towards left or right side. So this will lead to VTH shift. Now, the thing is, you can use these VTH shift for your advantage, or in your case, it might act as disadvantage. So it completely depends on the application. So these are the two conditions which are solely possible. Okay. So now talking about the MOSFET, right? So we know there are two types of MOSFET, NMOS and PMOS transistors. And if I talk about symbols or representation of these MOSFETs, so symbols or representation of these MOSFETs. So these MOSFETs are, first of all, okay. So let's see, this is NMOS and here is PMOS. So NMOS and PMOS, we represented as gate, source, drain, gate, source, drain. Generally, we don't show body terminal considering that body is shorted. Otherwise, there will be an additional terminal, which is the body terminal present over here. So this is one way of representing the MOSFET. Another way is by using the current direction. Okay. So in case of NMOS, the current flows from drain to source. In case of PMOS, the current flows from source to drain. Okay, so this is very important to understand because we know that the charges, either electrons or the holes, will be flowing from source to drain in both the cases. But We know that the current direction is opposite to that of electron flow direction and current direction is same to that of whole flow direction. So that's why when we say the current that is flowing in NMOS, the current is from drain to source, whereas in case of CMOS, the current flows from source to drain. It is very important to identify the terminals because we will solve the problem based on these terminals only. So these terminals identification is very important for you to solve the problem. Am I clear? Is it clear to everyone? Okay, so hope there are no doubts. Now moving on. Okay. So if I talk about MOSFET, so you see, considering this particular MOSFET, let's say a normal MOS, per se, whose gain and gate terminals. So if you see, so it has, this is the input terminal or input port, I should say, and this is the output port, correct? So now when you have one input port and one output port, the characteristics that are possible as shows input characteristics. Input characteristics means input will be voltage, input voltage and versus input current. So that means here input voltage will be IDS versus VGS. So this is input characteristics. Okay, in this particular configuration. Second is output characteristics. Here output current versus output voltage. So IDS versus VDS. Right? And there is a third characteristic which is known as transfer characteristic. So in transfer characteristics, it will take one parameter. Basically, we will be dealing with voltage and current, right? So it will take one parameter from input and another parameter from output. So in transfer characteristics, we will have IDS versus VGS. Okay? So these are the three characteristics. Now, if we talk about MOSFET, so in MOSFET, gate has an insulator, right? So it breaks the flow of current. So the IGS is always zero, ideally, until you have like you have applied such high voltages that it leads to oxide breakdown. Until then, your IG will always be zero. So that means, how will your input characteristics look like if I have to draw? The input characteristics is IGS, VGS, and it will always be zero. Correct? So this is the input characteristics. Now talking about output characteristics. Okay. So in output characteristics, we have IDS and VDS. So how your current changes with like output current changes with your output voltage. So how it changes, if we draw, so what happens? This is after threshold voltage, right? So we have like applied VGS greater than VGS. So your MOSFET is on. Because to turn on your MOSFET, you will need a minimum gate voltage or VGS of threshold voltage. So after applying the threshold voltage, you will see the current flowing, right? So this is for VGS greater than VGS, right? So here what happens? Slowly the current starts rising and at the end it saturates. So in this particular straight line region behaves linearly. So that means LDS is directly proportional to VDS. Here it is like transport, like we can say transfer region. So here it is neither linear nor saturated. So it's a sub-saturation region, and here it is saturated. So when we say saturated, that means the current does not change with the applied voltage. And in this particular region, it behaves like a current source. So what is ideally a current source? So current source means whatever voltage you apply across that particular current source, it will give you a fixed amount of current. And the same behavior is observed in the saturation region. Okay? So that's why whenever a MOSFET is in saturation region, it can be used as a current source. And in linear region, okay, so when current and voltage are linearly proportional, so what is the component where I is directly proportional to V? Yes, in our electrical, what is the component where I and V are directly proportional? Anyone?
Resistance.
Yes. So here it behaves as a resistor. So in the linear region, your MOSFET will behave as a resistor, simple resistor, whereas in saturated region, it will behave as a current source, right? So we say this is input characteristic, this is output characteristic. Now one of the most important characteristics and the MOSFET is the transfer characteristic. So we'll look into that. ID versus DCS. IDS versus. So now, as we know that in MOSFET, uh, in the enhancement type MOSFET, where uh, you have to create the channel, what happens is you will need a certain amount of voltage for the channel formation, correct? We discussed this last time also, that you will need a certain amount of gate voltage for the formation of channels. Beyond that voltage, you will see the current flow. So, let's say we call that particular voltage where the channel is properly formed as threshold voltage or VDS. Okay? So the behavior is current is almost zero. Then after threshold voltage, the current starts increasing. And current increases in quadratic nature. Okay? So this is quadratic in nature. Right? But the point is there any current in this particular region? So what do you think? Is there any current in this region? What about this region? Is the current zero or is there some current? What are your guesses or your opinions? Will there be any current below VTH or it will be zero?
Ideally, it should be zero.
Ideally it should be zero. Okay, so practically speaking, we say that this channel is formed beyond VTH, right? But before VTH also, while the process of Gandhi formation, there are still two charges, right? And those charges will definitely lead to current flow, correct? So, if we actually observe this graph in logarithm, so let's say this is VTH. So before VTH, actually the graph or the current is exponential in nature. The graph is exponential in nature, then it is quadratic, right? So here it is quadratic in nature, whereas in this particular region, it is exponential. Okay? So in subthreshold region, we call this subthreshold region, that is VTH less than VTH. So before VTH, we have subthreshold. In subthreshold region, the current actually follows an exponential nature, the exponential behavior. Whereas after threshold, it takes up a quadratic form. So this is very important. Please keep this in mind that in subthreshold region for a MOSFET, the current follows exponential behavior, and after VDS, it is quadratic in nature. Clear? So these are transfer. Now, since we have to solve some numericals, it is very important for us to understand the formulas, right? Or to know the formulas. So let's quickly look into the formulas. I'll write the formulas for both NMOS as well as CMOS. So first of all, in case of NMOS, the first thing that needs to be there is your MOSFET needs to turn on. So how your MOSFET will turn on? So for that, your VTH should be greater than VTH. So this is first important criteria that your MOSFET is turned on. So this will lead to on state. Okay. Now your MOSFET has turned on. Then the situation is okay. So if your VGS minus VTH is less than VDS, so if you observe VGS is input parameter, VDS is output parameter. So here we are comparing these two, input and output. So this is somewhere from transfer. Okay. So this is the relation between input terminal parameter and output terminal parameter. So in this case, we call it linear. Now, this is the linear that we mentioned over here, right? So this is the same linear that we are talking over here. Clear? So this linear and this linear are same. Now, the third condition is VGS minus VTH. Wait. Here VDS is greater, right? So if VDS is greater, then it is this is linear. That means smaller VDS, larger VDS leads to saturation. And this particular point where it changes, it is VGS minus VTH. This particular point, VGS minus VTH. Okay. So these are the conditions for linear, on-state, and saturation. Now we talk about the formulas for current. So If VGS is less than VDS, then we call it cutoff. Here IDS will be 0. Now VGS greater than VTS and VGS minus VTS is greater than VDS. So this is the condition for linear. So here we will write IDS as here. So if we talk about the simple current equation, the simple current is like IDS equal to non-C of W by S VGS minus VDS of whole square. So VGS minus VDS minus VDS by 2 into VDS. Yeah. So this is the formula, basic current formula. Now this can be used for linear, or let's say your VGS minus VDS is much larger than VDS by 2. Then we can simply eliminate this VDS and the formula will become IDS equal to non-C of W by L VGS minus VTH into VDS. Okay, so this is for this condition. It's much greater. Okay, this can also be used in linear, but if, like, let's say this is the condition, then we can further simplify the formula. Now coming to the third situation where VGS is greater than VTS and VGS minus VTS is smaller than VDS. This is the condition for saturation, and here we will have IDS as non by L VGS minus VTS whole square. So what we did, we basically substituted So we basically substituted VDS as VGS minus VDS. In place of VDS in this particular formula, we have substituted VDS as VGS minus VDS. Clear? Now, in the similar fashion, we will have the equations for CMOS. Now here we know that in case of NMOS, if we apply VGS as positive, then PMOS it will be opposite side. So that means VGS should be negative. So that means VSG would be positive in our case. So here VSG should be greater than mod of VGS. This is because the signs are important, like plus or minus, so that's why mod of VGS. Now, so this is for on-state. Second, VSG minus mod VGS should be greater than VSD. Please pay attention, I have interchanged, like earlier it was DS in case of NMOS, now it is SD, okay? So this is the case for linear, and third, VGS, VSD minus mod VGS should be less than mod VSD. This is the condition for saturation. Now same equation will be applicable for CMOS also. It's just that in case of VGS minus VTS, it will be VSG minus mod VTS. That is the only difference. Like in case of DS, it will be SD. In case of GS, it will be SD. And VDS is negative, so we will be using null to keep the formulas intact. Is this clear? Any doubts in the formulas or anything? Okay, I hope this is clear. Now let's move on to our first problem for today. So the first problem is, yeah, so this particular thing I have written, right? Mu P of W by L, this can be denoted by K. Sometimes mu P of W by 2L is denoted by K. Okay, so please pay attention, but K is basically constant since all of these are constant once the device is fabricated. That's the thing. So here if you observe, here, so first of all, this is a P-type MOSFET, right? So that means this is source, this is drain, and this is gate. And here the current equation is minus K. Why minus? Because this is for like P-type. So that's why minus K. VAC minus VT of whole square. So here we understand that K is mu P Cs W upon 2L, and this is an saturation. From the given equation, it can clearly be observed that the transistor is in saturation. And how do you identify a saturation? So here if you see your VG equal to VD. So that means VSG is equal to VSD. So VSG minus mod of VTH would always be less than VSD, correct? Here, do you understand how this is coming? See, VG and VD are shorted. So, and S is the common terminal. So, VSG will be equal to VSD. Just considering this as the input port, G and S, and D and S, this is the output port. Clear? So, VSG minus mod of VTH will always be less than VSD. So, this condition, now from here, what is the condition? See, VSD mod of VTH is always less than VSD. So that means it is a saturation. So even if the formula was not given, still we could identify that okay, the transistor is a saturation. So it is first of all, we have to find out what is the situation of VGS. Like is VGS greater than or VSG greater than VTH or not? First transistor needs to be on. You have to check that in the very beginning. Now second thing is to identify whether the transistor is in linear condition or linear region or a saturation region. Because we'll be applying the formulas according to the region of operation. Now here since it is in saturation and the formula is already given, it is mentioned that K is 28 millisiemens, VT is 0.9 volts. So here VT is similar to the VT that we observed earlier. And given that VS is 1.9 volts and small vs is 4 millivolts. Now what is the small signal current ID? Okay, so first of all, this is DC current. Okay, so all these formulas are for DC. When we write in capital letters, so the notations have certain importance. Like when you mention capital V, capital I, those are for DC. Whereas when you go for small v and small I notations, they are for AC applications. So this is DC voltage. whereas this small one is AC voltage. Now it has been asked to find the small signal current, the small ID. So first of all, what we will do, we will find the DC current, ID DC. Okay. How do we find the DC current? Using the given formula, it is minus K VSG minus VT of whole square. So Vs is 3.3 volts. So what is VSG? So this is minus 28 millisiemen. It is 3.3 minus 0.9 minus 1.9 because V is equal to V2 equal to VT. So that's why this is minus 1.9 minus VT or minus VT, which is 0.9 per whole square. So what is IDC that we obtain? Yes, what is the value of IDC that we obtain? So you can find out, right? Simply solving this, like what is the DC current that we obtain. Now, see, we have the current as this given already. Now let's say I find DI, that is small change. Small change, okay, this is 7 milliamperes. Right. Now we want to find the small ID, right? So let's say we have small dID upon dVs. This is known as Gm. Okay, that is conductance. And this conductance can be given by simply deriving this formula, right? So it will be minus K Vs Gm minus Vt by 2. Sorry, into 2 times minus Vsg, where is uh, can be written as Vs Vs minus Vs minus Vt, capital Vs minus Vt. So now, if we observe the small change in ID and small change in Vs, so ACs are these small changes, right? So small change can be written as to this small dVs. Let's say this is capital ID, capital V. Now small changes can be written as small ID by small V, right? Change in ID is small id, change in Vs is small Vd. It is also equal to your AC. So this is 2 times of K Vs minus Vx minus Vt. So small id is minus 2K Vs minus Vx minus Vt into small Vs. So from here we can find the small id, right? So first of all, how many of you understood how we are getting this formula? Like how we are approaching to this?
Can you
Any
explain how ID
sorry,
equal to 7 milliamperes? Can you
sorry, sir.
explain?
Your
Hello.
voice is not clear. Yeah.
Yes, I'm audible.
Sorry.
I'm audible now.
Your voice is breaking, but yeah. So what are you saying?
Yes, can you explain the formula where D by capital D by dVx equal to Gm equal to minus 2k into VSC minus VT? Can
Okay,
you
okay.
explain how?
Yeah, yeah. So
Yes,
actually we know it is minus k VSG minus VGS whole square, right?
yes,
And also this minus will also be cancelled because G वाला minus जो होगा ना, this minus VX, वहाँ से that minus will appear. So this minus is of no use for us. So here now we have to simply so equal capital ID differentiated with capital VX. And in this formula, we know Vg equal to Va, correct? In the current formula
yes, ma'am.
here. So we simply derive the current by using Vg as Va. When we derive it, so Id is minus K, Vs minus Vx minus Vt whole, right? Now this has been differentiated with Vx. So from there we get this formula.
Yes, ma'am.
Got it? Now derivation of ID with Vg is so current upon voltage gives you conductance. And since this is ID by Vg or Vx, we call it transconductance. So that's why it is denoted by Gm. Okay, so this is the transconductance. And now once we differentiate it, we are saying that small change in current is denoted by small id, small change in voltage is denoted by small v. Okay, so between small signals are always like small change or small inputs are generally signals. So we call them signals or inputs. So they are not DC. So that's why we change it like D capital ID to small id. And from there we started. Clear? I hope this is clear. Any doubt? Okay, if you have doubts, you can ask. But yeah, so the answer is 112 microampere. So moving on to next problem, question number 2. In this, again, it is a CMOS. Now here, see, here in this particular problem, there was no extra resistor in the drain side, but here you have this RD present. Okay, so in this problem, again, it is given as K as 28 milliseconds, VT is zero point 0.9 volt, this is source, drain, gate, and VS is 3.3 volt, RD is also given, it is 3.76 ohm. Now considering the device model as given above, what is the magnitude of current ID? So this ID means capital ID. So some similar situation again. So here also the transistor is in saturation. The current will remain the same. VSG minus VT whole square. Also, the same ID will flow from this, right? The ID that is coming from here, the same ID will flow to ID. So if I take this point as my VT, so VT is ID into ID, right? The current flowing across this is ID, and the same current flows through this as ID. Now we know VG equal to VD, right? So ID is minus K Vx minus Vt minus Vt whole square, that is minus K Vx minus Vd minus Vt whole square. So that means it will be minus K Vx minus IDRD minus Vt whole square equal to ID. So that means ID by K. So we can do, like, we can solve it in many ways. So we can make a quadratic equation. So quadratic equation will be easier to solve. So let's solve it in quadratic fashion. So it is 3.3 minus ID RD minus 0.9 square. So ID is minus 2.4 minus ID RD whole square. So this is minus ID equal to K 3.4 square minus ID and plus ID RD square minus 2 into 2.4 into ID RD. Now here RD also is known. RD is 3.76 kilo ohm, right? So here we have to solve this quadratic equation. So can you quickly solve this quadratic equation? So you know K, you know RD. K is 28 millisiemens. So how many solutions you will get for RD? Since it is a quadratic equation, you should get two values for ID, right? So can you quickly solve and let me know what are these two values of ID? What are these values? Okay, since you people are solving, so maybe I can let you know the values first, and you can solve it later to check whether you are getting the answers or not. It is 0.6 milliamperes and 0.68 milliamperes, right? Now, we have two solutions. ID is zero point 0.6 milliamperes and 0.68 milliamperes. Is it possible that in a single circuit, when there is certain voltage applied, then you can get two currents at the same time when all other voltages and everything are fixed? Can you have two solutions at a time? Is it practically possible? Yes, what are your opinions? Is it possible to have two solutions at the same time?
No, ma'am.
No, right? So you can have only single solution. So out of these two, either this is wrong or this is wrong. Any one of the two is wrong. Now how to check that? So first of all, see this particular circuit. So let me do it in this circuit. Yeah, so let's say I paste it here. So this particular circuit that we have here, now this particular circuit should satisfy the conditions, right? Because the transistor needs to be in on condition and secondly it should be in saturation. So first of all, here VSG should be greater than mod VTH, correct? So that means 3.3 minus ID into 3.76 should be greater than 0.9. So now in this place of ID, put both of them, right? 0.6 and 0.68. So which of the two satisfies this condition? Yes, if you substitute zero point 0.6 and 0.68, which of these two are satisfying this condition where it should be greater than 0.9? Come on, which one? 3.3 minus ID into 3.76K. For 0.6, what is the value you are getting over here? Yes, what is the value? Okay, so here you will get it as 0.9, 1.044, which is greater than 0.9. So that satisfies this equation, whereas in other case it is 0.74, which is less than 0.9. So this is not the case. So final answer will be 0.6 milliampere. Did you understand how to solve it? Yeah, it is 1.044. So did you get it? Like how to solve this kind of problem? And when you get multiple answers, how to obtain the correct answer out of those? Okay. So after this, if there are no questions, if you have any questions, please unmute yourself and ask. Now coming to this third problem. So here, first of all, what type of MOSFET is this? Yes, come on.
NMOS.
Yes, this is NMOS. So that means this terminal is source, this is drain, and this is gate. Now here, see, again the current formula is given, ID equal to K VGS minus VT whole square. By looking at the current formula, what is the MOSFET operating condition? What is the region of
Such saturation region.
saturation region? So this is again a saturation. Okay. Now you know that R1 is 100 kilo ohm and R2 is 575.7 kilo ohm. So by looking at these resistors and this being the resistor divider circuit, from here also we can see that the voltage that will be observed across VT will be much higher than VT, that is 0.5 volts, correct? So that means your transistor is in on state. And here it is given that K is 1.16 millisieverns per volt. So the question is, you have to find RD max such that this device remains in saturation. So How do we find whether the device is in saturation or not? What is the condition for saturation? VGS minus VT should be less than VDS. Correct?
Yes, ma'am.
Correct, sir. Now, let's find out what will be the VGS. What is the VGS? So, how do we find the VGS? It is 5 into 575.7 upon 575.7 plus 100. Right? So, the VGS that we obtain is 4.26. Is it 4.26 VGS? Take it once again. So the VGS that we will observe is 0.74 volts, right? Which is greater than 0.5 volts of VT. So VGS minus VT is how much? 0.24 volts. So this is 0.24 volts. And let's say equal to also VD minus VS. So here it is grounded. So let's say VS is 0. So that means 0.24 volts should be less than or equal to VD. Now this VD, how would you write VD? So this is VD. This is 5 volts. It carries a current ID. So can I write VD as 5 minus IDRD? I can write my VD as 5 minus IDRD, correct? Any doubts in this? No doubts, right? Hopefully this is clear. So ID we can find from this formula. ID is 1.16 into 0.24 square. So the ID will be 0.067 milliampere. So this is ID. Now 0.24 volts less than equal to 5 minus ID RD. So for RD max, like for maximum RD condition, your 0.24 volts should be equal to 5 minus ID RD to keep it in saturation. Correct? So simply 24 5 minus 0.24 by 0.067 milliamps will give you RD max. So RD max turns out to be 71.04 kilo ohm, and RD should be always less than equal to 71.04 kilo ohm. Is it clear? Anyone has any doubts in this? Hope there are no doubts. Just in case if you have any doubt in the solution, please ask. Okay? So coming to step number 4. Now in the same problem, Yeah. So in this problem, it is given that RD is 35.5 kilo ohms. What is the maximum ID that will flow through the device such that the device is in saturation? For this problem, ignore the earlier values of R1 and R2. Give your answer microampere. Okay, so RD is given. For saturation, again coming to the similar condition, VGS should be greater than VT and VGS minus VT, VGS should be less than VD and ID is K VGS minus VTS whole square, right? Is equal to relation. So here we want maximum current. So for maximum current, if there is a maximum current, then the drop across this will be maximum. So VDS will be minimum, right? Do you understand this? So here you have some current sign ID, RD, and you have plus minus VDS over here. Okay. This 5 volts only can drop across it. Now, if I write the KVL, I will write it as IDRD plus VDS. Correct? Now, I want to find maximum current. This 5 volts is fixed. So, if my current will reach to maximum, that means my drop across this RD will increase. So, this will increase. So, ultimately, this will reduce. Correct? So that means I should assume the smallest possible saturation value for VDS. So that means VDS is equal to VGS minus VDS. This is the smallest possible condition for saturation for VDS. Correct? So with this we will start. Now, okay. So VDS is VGS minus VGS. So ID equal to K times of, if I substitute this in this, it will become VDS squared. So that means, yeah. So now, if I substitute it here, I will get 5K. This is for VDS max, right? ID max. So 5 volts equal to ID max into RD plus, in place of this VDS, it will be root under ID max by K, right? So we have to solve this equation to find the ID max. So we can solve it by squaring on both sides. If we do squaring on both sides, we will get 25 equal to ID max ID plus ID max by 2 plus 2 ID max square ID by 2. So we have to solve this particular equation. Here everything is known, like you know ID, you know K from the previous equation, every previous question, that is 1 point how much, 1.16 milli, yeah, 1.16 millisieverts So with this, we will get, again since it is a quadratic equation, we will get two values for ID max. So one value is 131.365 microampere. Another value is 151 microampere. Okay, so these are the two values. Again, we have to screen between these two to find the correct answer. So we know that VDS is VDD minus ID max into RD. So here this value should come positive, right? Because VDS cannot be negative. So we will check in which condition we are getting positive. So turns out that in this particular situation we get positive VDS. So that means this is the answer. Okay, so this is the answer. 131.365 microampere. Is this problem clear? How we approach this problem? Yes. Is this clear? Any doubts in this? No doubts, right?
Yes, ma'am. Yes.
Okay. So yeah, you've had some doubts, so please ask. Otherwise, we'll move to the next.
Ma'am, can you show the slide again? Okay, done, ma'am. Done.
Okay, I'm moving on to the next problem. Okay. So again, for the same problem. Now here it is given that R1 and R2 are used from previous problem. That is question number 3, which was 100 and 575 pounds. 575 pounds 7K. And RD should be used from here, that is 35.5K. And 5K, this is 24.8. So in this particular problem, due to temperature and other device imperfections, the value of K is no longer the stated value in question number 3, but 3 times. So the new K dash is twice of K. Okay. So that means K dash is how much? So it was in question number 3, 1.16 milli. 1.16 millisiemens per volt into 3. So which makes it 2.36 millisiemens per volt K dash. So the question is, will the device be in saturation with this new value of K? So again, for saturation conditions, we know VGS minus VGS should be less than VDS. Correct? Now here, what is VDS? VDS is VDD minus ID ID. Correct? So VGS minus VDS is how much? We already found out. For this, the VGS was 0.24 volts. Should be less than equal to P minus ID RD. So what is the value of ID? It is K VGS minus VGS square. So that was 2.32 into 0.24 4 whole square. So ID comes out to be how much? ID comes out to be 0.1336 milliampere. So this is the ID that we get for the new K dash. Now with this ID, we have to find, okay, so the VDD is 5, not 3. Yeah, it is 5. So ID into RD, that is 0.1336 into RD is 35.52. This is milli. So this ID into RD is, yeah. So this ID into RD will be substituted here. So VDS is 5 minus 0.1336 milliampere, 35.5 kilo. So VDS turns out to be 0.378 volts. Okay. So now VDS turns out to be 378, which is greater than 0.24, that is VDS minus VDS. So that means what is the operating condition of the MOSFET? If this is the condition, then what is the operation of MOSFET? Region of operation, yes. What is the region of operation? When VDS is greater than VGS minus VGS.
Saturation.
Saturation. So what was the question asked? Will the transistor still be in saturation? So the answer is yes. Got it? So these are very simple problems. We have to just apply the formula and just the basics. Right? Okay. So moving on to the next problem. Problem 6. So in this problem, now see here, what has changed from the previous problem? Again, it's an NMOS. But you see here, there is another resistor which has been introduced, which is RS. Now, until now, what we are doing, VGS or VDS, we were saying that VS is grounded and 0. But here you observe your VS is not 0 because your VS will be here. So your VS is floating. Now it is not so easy to get your VGS or VDS. Getting my point? So in this problem, now let's see how to solve this problem. Okay. And you will also see the importances of these resistors also, like RD, RS, how things change with when, etc. So here ID is again VGS minus 4, K is 4.7 millimeters per volt, VT is 0.8, R1 is 654, R2 is 327, RS RDR 22.72 each. Now solve this circuit. Arrive at the operating point with the MOSFET. What is the ID? Give your answer. Okay, when it is asked to give the operating point of MOSFET, so operating point basically means VGS, VDS, ID. So whenever you are asked to find the operating point, you basically need to find VGS, VDS, and ID. These are the operating points, operating conditions. And based on these two, you will find the region of operation also. Right? So first you need to identify VGS and VDS. define the region of operation, and based on that, you will again find the current using the formula required. So now, first here you will find Vg. Now I'm not writing Vg yet because here S is floating. So we will only be able to find Vg with respect to ground. So this will be 5 into 327 from 654 plus 327. So by solving this, we will get the value of Vg, which turns out to be 1.67 volts. Okay. Now, so this will give Vg of 1.67 volts. Next step is VGS, because VGS is the one that is important. So the current that is flowing from this VDD till ground, we call it ID. So the same ID is flowing through RD also and RF also. So VGS will be 1.67 minus ID into RF, as VS is ID into RF. Correct? So this is your VGS. Now, if we see how we will write ID, that is K VGS minus VT whole square. That is K 1.67 minus IDRD, sorry, IDRS minus 0.5 whole square is ID. So again need to solve this quadratic equation. After quadratic equation, so we will again find two current equations, okay? Two current values. So one value is 47 microampere and other value turns out to be 56 microampere. So out of these two, one value is correct that we have to find out. So for saturation condition, we know, or let's say for normal condition from the very beginning, we know that VGS should be greater than VGS, right? So it is 1.67 minus IDRD should always be greater than 0.5 volts. So what happens when we substitute this value, it gives us a greater value, whereas this value, this lesser value. So that means with this value of current, your transistor won't be on. So saturation to बहुत दूर की बात है. So this is the first condition that you should check is whether the transistor is on or not. अगर दोनों ही condition में on आ जाता है, so then move to the condition of saturation. Okay. So the final answer of ID turns out to be 47 microampere. Is this clear?
Yes, ma'am.
Okay. Now move on to the next problem, question number 7. Okay, so in the earlier circuit, compute the small signal GM for the given MOSFET. So small signal GM, what did I tell you? What is GM? So DID upon DVGS will equal to GM. So that is DQ VGS minus VT square upon DVK. So it turns out to be 2K VGS minus VT. This is your GM. Okay. So this will be GM equal to 2 into what is the Q? 4.7 VGS Or yeah, so VGS minus VGS minus VT, if you find out, it is 0.06 0.603 minus 0.5. From here, gain turns out to be 0.91 millisiemens. Or you can again modify this formula, like multiplying and dividing it with VG minus VT. So क्या हो जाएगा 2 times VG minus VT into VG minus VT upon VG minus VT. So your GM will be 2K ID upon VG minus VT. So both the formulas are correct. You can use any formula you want. Is it clear? Okay, moving on to next problem. Question is, so in this circuit, question number 6, the structure has been modified by introducing capacitors in this particular case. So what happens is, when there are capacitors present, these capacitors are so large that they behave as short circuits for time varying signals. Okay, so behave as short circuits for time varying signals, like for AC, they are all shorted. Assume the mass right characteristics as perfectly flat in the saturation region, that is no dependence on VDS whatsoever. All the resistor values and device parameters are given earlier. What is the small signal gain of the circuit? So here it is mentioned that you have to consider small signal gain means small signal input versus small signal output. So that is V out by V in is what you need to find out. Okay, small signal means AC. So here this particular capacitor will be shorted, this particular capacitor will be shorted, this will be shorted. So the resultant circuit will look like R1, R2, RD, and here we have V out. From here we will get Vn. As I mentioned earlier, that what I said that we will put this to AC ground, right, while performing AC analysis. So since we are performing AC analysis, we will put that to ground, and the gain, small signal gain for this particular configuration, this is known as CH amplifier, that is common source amplifier. Here source terminal is common between input and output pole. That's why it is common source amplifier. Okay. So here the gain is given by minus Vm into RD for this particular configuration. So you need not to remember this formula. You can always solve the circuit by using small signal, like small signal model. So you have to like convert this particular circuit to a small signal model, and from there, when you solve the V in versus V out, you will get this formula. So you need not to remember it always. Okay, so this is the formula that you get after solving. So now we already know that GM is, we solved it earlier, it was 0.91, 0.91 millisiemens, and RD was 22.7 kilo ohms. So with this, the small signal gain turns out to be 20.7 volts 1 volt. Now, if we want to calculate it in decibels, so it will be 20 log 20.7 45 volts. So milliamp per VM is 26 decibels. Any doubts in this? So this is basically the formula that you get. The solution is already, so the derivation has been mentioned in the lecture, so you can check the lecture also. In case if you don't understand, you can ask me so that I can explain you how you get this formula. Okay. So hope there are no problems. Moving ahead, we have question number 9. In this question, so again, similar formula, like similar circuit. This is again an NMOS, so this will be drain, source, gate. So, and generally in this configuration, this will be your output and this will be your input. So in your MOSFET, now since we are talking about these, so if I talk about the MOS amplifier configuration, so it's like gate, drain, source, correct? Now let's say you can, so first of all keep that in mind that you can use gate and source for input. Gate and source terminal can be used for input. Similarly, drain and source terminal can be used for output. That means source terminal can be used to take take output or provide input to the circuit. But gate, you can never take output from the gate terminal. Similarly, you can never give input to the drain terminal. Keep that in mind. And when I'm talking about inputs and outputs, I'm talking about small signals. So that means AC signals. Okay? So
Yes,
now,
ma'am.
okay, so first, if we talk about first configuration, so here, let's say you are giving input to gate. So here you give your input. This is drain, this is source. You take output from drain. Okay? If you give input to gate and take output from the drain, so you see here the source terminal is common for both gate as well as drain, right? So this is common source amplifier. If you observe a transistor connected in this type of configuration, then this is common source amplifier. Clear? Now second, again you have same MOSFET in type source, drain, source, gate. Now let's say you give input to source, okay, and you take output from drain, right? So here one terminal that is not being used here is gate. So this configuration is known as common gate configuration, a common gate amplifier. Okay, common source, common gate. Now, since there is third terminal which is left, so let's replace this as well. So here again this is gate, drain, and source. So what we are doing is we are giving input to gate, but we are taking output from source terminal. Okay. So here the terminal which is left alone is common drain. So this is common drain amplifier. Now we will see whether it is an amplifier or not. So what do you mean by an amplifier? What should happen if there is an amplifier? So there are two things, right? If gain, that is V out by V in, is greater than 1, then it is amplifier. But if V out by V in is less than 1, that means your output comes out to be less than 1, then it is attenuator. Clear? So now we understood that there are three configurations, three types of amplifiers possible using this single MOSFET, depending on where you provide the input and where you take the output from. But all these three have different behaviors, like depending on phase shifting, on amplification factors. So all of them are different from one another. So in future classes, in future lectures, we will solve problems on all these particular configurations, and we'll also understand their behavior, right? For now, what is the configuration? Until now, we have solved these many problems, right, till now. So what is the configuration that we have observed till now? Where were we giving input and where were we taking output from in all these problems till now?
Common source amplifier.
It was common source because we were always giving, or we were talking about gate terminal, and we were saying VGS, right? VDS. That means source was common in all the cases. So until now we have only observed common source amplifiers. But in future classes we'll look into common gate as well as common drain configuration also, and we'll look into their properties as well. Right. And also, in case of common source, one thing that you need to understand is common source amplifier introduces a phase shift of 180 degrees. That means your input and your output have a phase shift of 180 degrees. So that means there will be a minus sign in the gain. So the gain will be negative in case of common source. So negative gain basically means, so I'm not talking about decibels, okay? I'm talking about volt by volt gain. So if you have a negative volt by volt gain or negative current by current gain, that means there is a phase shift of 180 degrees. Am I clear?
Yes, ma'am.
See,
Yes, ma'am.
180 degrees phase shift, and the gain greater than 1. So this is the property of common source amplifier. When we talk about common gate amplifier, here again gain is greater than 1, but you don't see a phase shift. So no phase shift. Okay? And common drain is not actually an amplifier, rather it is an attenuator. So here Please keep this in mind. Gain is always less than 1. Maximum you can obtain is gain equal to 1 in this particular case of common drain amplifiers. But practically speaking, gain is always less than 1. Am I clear? So these are two principal properties of heat consideration. Now moving ahead. So yeah, in this particular, again, so here you see we have input from gate and output from drain. So this is a common source amplifier. So this is again a CS amplifier. So in this CS amplifier, it is given that mu P of W by L, that is KW by L, is 1 milliampere per square. VTHN is 0.5 volts. Lambda is 0. So lambda, what is this lambda? We need to understand, right? So as we observe that an output characteristic, we said that for VGS greater than VTS, for smaller VDS, your current rises linearly, but as it reaches VGS minus VTS equal to VDS, it saturates, right? And we said that current does not change at all, right? This is what I explained to you earlier, no? But now see what happens. Practically, this is not true. We want ideal current source type of behavior. We do get that, we do get this current source behavior for very large transistors with longer channel length. But in smaller transistors, we all know that with increasing demand, the reduction in the transistor size is very critical and very important. The transistors are reducing, the number of transistors the size of transistor is reducing day by day. So with this reduction in transistor size, the challenge that comes is obtaining this ideal current source behavior. So because of this reducing size, we call that second order effects come into picture. And one of the common second order effects that come into picture is channel length modulation. So in this, what happens, because of the smaller size and already applying negative voltage, your channel length starts reducing. And because of this reduction in channel length, rather than the current being settled, the current starts increasing. Okay. So this is for lambda not equal to 0, and this comes due to channel length modulation, which is called second order effect. You can study them. There are many second order effects. One of them is channel length modulation, because of which you get this lambda not equal to 0. There is, in this blue line is lambda equal to 0. So wherever it says that lambda equal to 0, that means that is being talked about an ideal transistor or ideal MOSFET where current is saturated. Whereas when we see the value of lambda being other than 0, that means there is a possibility of channel length modulation. Okay? And when there is channel length modulation, definitely the formulas of current will change, that we'll observe in the upcoming questions. Okay? So yeah, here it is mentioned that lambda is 0 volt inverse. R1 is equal to R2. So these two are equal. So if R1 equal to R2, then it means VGS will be how much? If VDD is 2 volts, R1 equal to R2, then VGS will be 1 volt, right?
Oh.
Yeah. So VGS is 1 volt. Now the question is, find the maximum value of resistor R, this R, such that the N-channel MOSFET remains in the pinched off condition. Pinched off condition means saturation region. So here it is mentioned also, but pinched off condition means saturation only. So just in case if you see pinched off, please don't panic. It means saturation condition, right? So see, you know that your transistor needs to be in saturation. So again, if I say 2 volts, I write the KVL for 2 volts, considering the current ID, it would be 2 volts is ID into R plus VDS. Correct? Now we want to find the maximum value of RD. So practically speaking, 2 minus ID into R. So for R to be maximum, let's say the current is constant. Because VGS is constant, VT is constant, we are talking about saturation, so current will be constant. And I can find the current also. So ID equal to C of W upon 2L into VGS minus VT whole square. So that is ID equal to 1 by 2 into 1 minus 0.5. So that is ID equal to 0.5 milliampere. Correct? So this is the current that we observe. Now VDS is 2 minus 0.5 milliampere into R. So for maximum R, so first of all for saturation, what is the condition? VGS minus VGH should be less than equal to VDS, right? Now we want my R to be maximum. So if this increases, that means my VDS will reduce. So I should focus on the minimum limiting condition of the saturation. That means VGS minus VGS equal to VDS. So this is the condition that will give me R max. With this condition, I can find the R max. So VGS minus VDS, so how much is the VDS that we are getting? It is 0.5 volts. Correct? Now VDS is 0.5 volts. So substituting it here, we'll get 0.5 equal to 2 minus 0.5 milliamps into R max. So R max is 2 minus 0.5 by 0.5 kilo ohm. So that is 1.5 by 0.5. So R max is 3 kilo ohm. So maximum R max can be 3 kilo ohm, or it should be less than 3 kilo ohm. So the answer will be 3 kilo ohm. Is it clear how we solved this problem? Is it clear to everyone? How did we reach to this conclusion?
Yes, ma'am.
Yes. Okay. Now this is question number 9. This is question number 10. Again, similar problem. We see W by L is at 0.5 milliampere per volt. BPHT, because it is a CMOS, it is minus 0.5 volts. Lambda is again 0 volts in volts. R1 is 9K. RD is 18 kilo ohms. So find the value of R2. We have to find R2 such that ISD is 90 microampere. Okay, alright. First of all, here we know for on state, VSG should be greater than mod of VTH, correct? So VSG should be greater than mod of VTH. Now VT, if I want to find, what will be VT? It will be 2 into R2 upon R1 plus R2. This is my VV. So this is 90 amps. This is 18 amps. Now, okay, and we know RD and ISD, right? So what is VD? VD will be ISD into RD. So that is 90 microamps into 18 kilo ohms. So VD will be how much?
Hmm.
1620.
It will be 0.162 volts, correct? Right? VD is 0.162 volts, correct?
No, ma'am.
Okay. So VSD will be 2 minus 0.162. So this will be how much? So VSD is 1.838. So this is VSD. And VT is 2 times R2 upon R1 plus R2. And VSD would be 2 minus 2 into R2 upon R1 plus R2. This should be greater than or equal to VTH, that was mod of VTH, so it is 0.5. Okay. So here it is 2R1 plus 2R2 minus 2R2 should be greater than or equal to 0.5 R1 plus 0.5 R2. These two are cancelled. So 2R1 should be greater than or equal to 0.5 R1 plus 0.5 RT. So that means 1.5 R1 should be greater than or equal to 0.5 RT, which is 3 R1 should be greater than or equal to RT. So 3 R1, R1 was 9 kilo ohms. So should be less than 3 R1. Okay, so we are going to say greater than equal to R2, means R2 should be less than or equal to 3 times of R1. So that means R2 should be less than or equal to 27 kilo ohms. So this is one condition that we obtained from this, right? And another condition we will obtain from, like, okay, so if at all, like it is 3 times or less than 3 times, what will be the gate voltage here? It will be definitely more than 1, right? More than 1 volt. So G should be, so with this condition, it will be much higher than 1 volt over here. And we will check for saturation condition. That means your VSC should be greater than equal to VSC minus VTH, moderate VSC. VSC, you already know, 1.828. It should be greater than equal to VSC, which is 2 minus 2 into R2 upon R1 plus R2 minus 0.5. And here it is 1.838, which is an equal to 2R1 minus 0.5 R1 minus 0.5 R3 into R1 plus R2. And 1.838 R1 plus 1.838 R2 is greater than equal to 1.5 R1 minus 0.5 R2. Let's say zero point eight R1 on this side plus R2 is greater than or equal to 0. This R2 is greater than 0. So here,
मैम VD का जो वैल्यू है 1.62 होगा ना?
किसका?
VD
VD, हाँ VD 1.62 होगा.
यस मैम.
VD 1.6 का है, 0.162 है.
1.62 मैम.
माइक्रो, यहाँ पे माइक्रो एम्पियर है ना, 90 माइक्रो.
हाँ तो ठीक है मैम.
ओके, तो
1.62 आ रहा है मैम.
हाँ 90 था ना, इसके लिए तो 1620 आ रहा था ना.
यस मैम. यस मैम.
राइट है. तो यहाँ पे फिर ये चेंज हो जाएगा ना, तो उसकी वजह से फिर पूरा चेंज होगा. दिस इज 1.62. तो 1.62 होने से वी आर लेफ्ट विथ हाउ मच? 0.3.
0.38.
ओके, तो 0.38 होने से फिर यहाँ पे हाँ, that's why it was going wrong. इसके लिए सॉल्व कैसे नहीं हो रहा है? राइट, तो यहाँ पे इट इज 0.38 वोल्ट. तो 0.38 होने की वजह से इट विल बी 0.38 R1 plus 0.38 R2 should be taken equal to 2 R1 or let's take 1.5 R1 minus 0.5 R2. So moving this side and R1 wala term this side, we will get 0.88 R2 should be greater than or equal to 1.88 R1. Okay. So R2 should be greater than or equal to 1.88 upon 8.88 R1. So from here we have got two conditions, right? That is R2 should be less than 27 kilo ohm, and also R2 should be greater than this 1.88 by 0.88 R1, which is how much? It is 2.136. So R2 should be greater than or equal to 2.136 into 9, which is R2 should be greater than or equal to 19.22 kilo ohm. So R2 should be greater than 19 kilo ohm and less than 27 kilo ohm. ऐसा कोई है क्या? Okay, मैं तो are we missing some conditions from this? Maybe 3.5. Okay. Yes, I will let you know I have the condition. Are we going wrong somewhere? Calculation was सही था ना? DHT हमारा कितना आता है? Okay, so we are already starting considering. यहाँ पे हमने जब सॉल्व किया है, we didn't start considering current, right? कि ये saturation current है. We directly started using current, but we didn't use the formula for saturation. Because in the same question, if we solve it this way, okay, so it's like okay, solution 2, so the same effect, so if we start by assuming saturation, then ISC is 90 micrometers. So ISC can be written as Kw by 2L V VSD minus VTH square. So 90 micrometers is 0.552. VS was VS is K minus VK minus 0.5. I can do it. That is 90 micrometers 25 into 1.5 minus VK square. So from here, the value of VT that we obtain is 0.9 volt. But since we are already assuming saturation, so 0.9 volts are going to basically we get this as 0.9 is 2 into R2 upon R1 plus R2, right? So that is 0.9 into 3 into 0.9 R1 plus R2 into 3 R2. This is 0.9 times R1 is 1.1 times R2. R2 is 0.991 by 1.1. R2 comes out to be 7.36. But if VT is 0.9, VD was how much? VD was 1.60. 1.60. So VST is 0.38 volts. VST is 1.1 volts. So VST minus VTH is 1.1 minus 0.5. So this is 0.6 volts. So VST minus VTH is greater than VST, right? So that means assumption is wrong. So transistor not in saturation. Okay. So earlier we assumed that transistor was in saturation in this particular solution, and turns out that the transistor is not in saturation. So what we will assume now, अगर saturation में नहीं आएगा next step is let it be in linear. So second assumption is transistor is in linear region. ट्रांजिस्टर जब तक इज इन लीनियर रीजन तो आईडी का फॉर्मूला क्या होगा म्यू आर डब्ल्यू बाई वाई VGH minus VTH. So obviously it is CTV into mod VTH minus VSD by C into VAC. This is the formula. So here 90 micron K equal to Q was 1, no, Q was 0.6, 0.5 millimeter is 4 into VS2 minus VG minus 0.5 minus VST by 0.38. 0.38 by 2 into 0.38. So it is 90 microampere minus 0.5 4 into 1.3 minus and 1 minus. That contact इसको पूरा सॉल्व करने के बाद VG turns out to be 0.836 volts. VG turns out to be 0.836 volts. So 0.836 is 42 into R2 upon R1 R2. This will be 0.836 R1 equal to 2 minus 0.836 R2. So R2 almost turns out to be 6.5 coulombs. And again, if we check for this, so VGS is checked. So VSG is 2 minus 0.836. So that is 4, 6, 1.1. VSD, this is sigma volt, and VSD is 0.38 volts, and they are in linear. Is this clear how we got this? So earlier, the solution that I was trying, I didn't try to assume anything. Like I was not assuming the transistor in any region of operation, and I was trying to solve the equation. So there, what happened? We directly used the formula of current, but we didn't use the so we used the current in KVL, but we didn't use the MOSFET current formula. And unfortunately, this should give the answer, but there is something, some mismatch is happening because of which we are not getting the answer. Maybe we can check this again. But the second method in which we are solving this is we have assumed the transistor, let's say it is in saturation at first. We tried to solve it. We solved it, we got the result R2. But then the question is this even correct? So we have assumed the transistor to be in saturation. So is the transistor coming in saturation? So the answer is no. The transistor is not in saturation. We are getting it from this particular formula. So then we get to know, okay, the transistor is in linear region. So again, we are solving the current equation for linear region. And then when we solve it, we get the answer to be 6.5 kilo ohms. And again, if we recompute it again, so it's more like an iterative method, we see that we get it in the linear region. Did you get it? Is it clear? How we solve this equation? Or like how we solve this formula equation?
Yes, ma'am.
So this is how we have approached. So earlier, so this is one method, like by assuming it in the region. It's just that there is a possibility that maybe you can assume it in saturation and it may come out to be in saturation. But the caution here is you have to keep checking your answer. Like if you have assumed your saturation, at the end you have to prove that your answer is correct and your transistor is in saturation. That means you have to prove your assumption in this second method. Is it clear?
Yes, ma'am.
This method, we are not assuming anything. We are simply solving based on the equation. Just that there is something, like somewhere some calculation mistake must happen here. Otherwise, this will also give you the answers. But yeah, you will not get the exact answer here because here you will be getting it in the range, like greater than less than the range, you will get the answer, and that should fit in the given question. So the first method will give you the solution in ranges, whereas the second method, it will be a little longer because you have to check the regions of operation and assume and check, but it will give you the correct answer, like final answer. So both the methods can be used. So first method, maybe you can reiterate it again and check it once, like where there is a mistake, like if there is a calculation mistake or something. Yeah, if you have something, please unmute yourself and ask if you have some doubt. Somebody raised their hand, right? Can you unmute yourself? Hello. Okay. If there are no questions, maybe we can stop over here and meet again on the next week's lecture. Hopefully, there won't be any problem this time in the video recording. So I'll immediately upload the video on YouTube. And if you are subscribed, you'll get the link immediately after it gets uploaded. That's all.
Okay, ma'am. Thank you, ma'am.
Thank you, ma'am. Thank you. See you all next week.
Thank you, ma'am.